Okay, let's unpack this. Have you ever woken up after, a celebration with that distinct post-party haze, that headache, nausea, maybe suddenly really sensitive to light? We're talking, of course, about a hangover. The medical term for that delightful experience is vasalgia.
Yeah, Vasalgia. And today we're embarking on, well, a deep dive into the world of alcohols and phenols. We're going to explore their fundamental structures, properties, and, importantly, their reactions. Now, hangovers, they're multifaceted, right? Dehydration definitely plays a role, loss of vitamin B2. But the real chemical culprit, the one that makes you feel truly awful, that's acetaldehyde. It's this toxic product formed when your body oxidizes ethanol, the alcohol in drinks. And don't worry, we'll circle back to the precise chemistry of that hangover near the end of our discussion today.
Okay, good. So our mission today is basically to distill an entire chapter on alcohols and phenols down into the most essential bits. The core concepts, mechanisms, those reaction strategies you really need to know. Think of it as a shortcut to being well-informed. We want to focus on practical understanding, point out some common pitfalls, maybe things students often get wrong, and really dig into the core principles that matter if you're tackling organic chemistry. We're here to make this complex stuff clearer, maybe even engaging, highlighting the why behind it all. So let's jump right in with the absolute basics. What exactly are alcohols and phenols?
Okay, so at their core, alcohols are organic compounds that have a hydroxyl group that's an OH group attached to a carbon atom that's sp3 hybridized. Usually spot them because their names end in O well.
Right, like ethanol or methanol.
Exactly. Phenols are, close relatives, but there's a crucial difference. Their OH group is bonded directly to a phenyl ring, an aromatic ring, and that direct attachment gives them some really unique properties compared to regular alcohols.
Okay, so similar but different because of that ring attachment.
Precisely. And what's really fascinating is just how widespread these groups are in nature. It's
Oh,
incredible.
yeah. Give us some examples.
Sure. Think about alcohols first. Chloramphenicol, that's a powerful antibiotic used against things like typhoid fever. It has alcohol groups. Cholesterol, which is absolutely vital for making steroids in your body, that's an alcohol. Even cholecalciferol, which most people know as vitamin D3, essential for healthy bones, also an alcohol.
Wow. Okay. So they're in medicines, biochemicals.
Exactly. And phenols are just as important. Capsaicin, that's the molecule giving chili peppers their heat. It's a phenol. And tetrahydrocannabinol, THC, the main psychoactive compound in marijuana. That's a substituted phenol too. Their presence in everything from medicines to, well, spices really highlights how fundamental they are.
That's a great overview. So how do we actually name these things systematically? I remember the IUPAC rules for alkanes.
Yeah, and the rules for alcohols build right on that. It's pretty logical. You just swap the E at the end of the parent alkane name for all. The key things are, find the longest carbon chain that includes the carbon holding the hydroxyl group, and then you number that chain so the OH group gets the lowest possible number, the lowest locant. Oh, and if you have a chiral center, a stereo center, you have to indicate its configuration, R or S, right at the beginning of the name.
Okay, longest chain with the OH, lowest number for the OH, and specify chirality. Got it.
And while those IUPAC names are the precise official ones, you hear common names all the time.
Like rubbing alcohol.
Exactly. You'll hear isopropyl alcohol way more often than its IUPAC name, 2-propanol, or tert-butyl alcohol instead of 2-methyl-2-propanol. Benzyl alcohol is another really common one.
Right, those are definitely familiar.
And beyond just naming, we classify alcohols. This is super important for predicting reactivity. We classify them as primary, secondary, or tertiary.
Okay, primary, secondary, tertiary. How does that work?
It all depends on the alpha carbon. That's the carbon atom directly bonded to the hydroxyl group. You just count how many other alkyl groups, how many other carbons are attached to that alpha carbon. If there's one alkyl group, it's a primary alcohol. 2 makes it secondary, and 3 makes it tertiary. And trust me, knowing whether an alcohol is primary, secondary, or tertiary is absolutely critical because they react very differently.
That makes sense. So structure dictates reactivity. Let's shift gears a bit. What about some commercially important alcohols? You mentioned methanol earlier.
Yeah, methanol, often called wood alcohol, historically. It's produced on a huge industrial scale, millions of tons a year, but it's incredibly toxic. Ingesting even a small amount can cause blindness, or worse, it can be fatal.
Wow, but it's used industrially.
Oh, absolutely, as a solvent, a starting material for other chemicals. And interestingly, it gained some notoriety as a race fuel, especially at the Indianapolis 500 after a really bad fiery crash back in 1964 involving gasoline. Methanol's appeal. Its fires don't produce smoke, which makes them hard to see, but crucially, they're much easier to extinguish with water than gasoline fires. so arguably safer for the track environment, even though the fuel itself is dangerous.
Huh, I never knew that about race fuel. What about ethanol? That's the one people are more familiar with.
Right, ethanol or grain alcohol. We mostly associate it with fermented beverages, obviously. But industrially, it's often synthesized differently, usually by adding water across ethylene using an acid catalyst. And to avoid the heavy taxes placed on alcohol meant for drinking, industrial ethanol is usually denatured.
Denatured. What does that mean?
It means they add small amounts of toxic stuff, often methanol, actually, or other unpleasant chemicals, to make it completely undrinkable. That way, it can be sold tax-free for industrial uses like solvents or fuel additives. And then there's isopropanol, that rubbing alcohol you mentioned, another very common one, mainly used as an antiseptic, typically made from propylene.
Okay, so these simple alcohols are everywhere, but what really makes them behave differently from, say, alkanes? You mentioned properties earlier. Their boiling points, for instance, seem really high for their size.
They are. It's a massive difference. Take ethanol, like you said. It boils at 78 degrees Celsius. Compare that to ethane, which has a similar molecular weight. Ethane boils way down at minus 89 Celsius. Or even chloroethane, which is heavier, boils at only 12 Celsius.
So why such a huge jump for ethanol?
It comes down to one key thing: hydrogen bonding. That oxygen atom in the IOH group is highly electronegative. It pulls electron density away from the hydrogen atom. This creates a significant partial positive charge on the hydrogen and a partial negative charge on the oxygen. These partial charges allow alcohol molecules to form these really strong intermolecular attractions with each other called hydrogen bonds. It takes a lot more energy, a higher temperature, to break those bonds and let the molecules escape into the gas phase.
Ah, hydrogen bonding. That explains the high boiling points. Does it affect solubility too, like how they mix with water?
Absolutely. Those same hydrogen bonds are... Water, of course, is full of hydrogen bonds itself. Now, think about an alcohol molecule. It has two parts, really. There's the alkyl chain, the carbon part, which is nonpolar and hydrophobic, meaning water-fearing. And then there's the hydroxyl group, the IOH, which is polar and hydrophilic or water-loving, because it can form hydrogen bonds with water molecules.
So it's a bit of a split personality.
Kind of. And the balance matters. For small alcohols like methanol or ethanol, the hydrophilic OH group dominates. They can hydrogen bond effectively with water, so they mix completely. They're miscible. But as that hydrophobic alkyl chain gets longer, say in butanol with 4 carbons, the nonpolar part starts to take over. Solubility in water decreases quite a bit. Get up to something like octanol with 8 carbons, and it's almost entirely insoluble in water. The long, greasy chain just doesn't want to mix.
Okay, that makes intuitive sense. Longer chain, less water soluble.
And if we connect this to the bigger picture, you'll see this principle is absolutely vital in, say, drug design.
Oh, how so?
Well, take antibacterial agents. Research has shown that for simple primary alcohols, their ability to kill bacteria actually increases as the carbon chain gets longer, up to a point. The sweet spot seems to be around 8 carbons octanol again. Beyond that, the potency drops off sharply.
Why is there an optimum length?
It's a balancing act. You need a longer, more hydrophobic chain, because that helps the molecule penetrate the bacterial cell membrane, which is also lipid-like hydrophobic. But if the chain gets too long, the molecule becomes so insoluble in water that it can't even travel through the surrounding aqueous environment to reach the cell membrane effectively. So that 8 carbon length represents the best compromise. Hydrophobic enough to get through the membrane, but still soluble enough to get to the membrane.
That's fascinating. A perfect balance.
Exactly. And it also explains why branching the carbon chain often decreases antibacterial potency. A bulky branched chain might have more trouble slipping neatly through that cell membrane compared to a straight chain. You see this principle applied in compounds like hexylresorcinol, which you sometimes find in throat lozenges. It's a phenol derivative, and its optimal antibacterial activity is found with a 6-carbon chain attached.
So what does this all mean for you as a learner? It sounds like it's not just about memorizing structures.
Definitely not. This isn't just some random fact about octanol. It's a really profound principle in molecular design. It shows how chemists, and nature too, fine-tune molecular properties like solubility and membrane permeability to achieve a specific function, whether it's killing bacteria, delivering a drug, or acting as a solvent. It's all about optimizing that balance.
Right, understanding the why. Okay, let's shift focus now to reactivity. Let's start with acidity. Alcohols can act as acids.
They can, yes. That proton on the hydroxyl group, the H of the OH, is slightly acidic. It can be donated to a base. When an alcohol loses that proton, it forms an alkoxide ion, RO, which is its conjugate base.
How acidic are they, generally speaking?
For most simple alcohols, their pKa values are typically in the range of 15 to 18. Now, that means they're much more acidic than, say, alkanes or amines, which have pKs way up in the 40s or 50s, but they're still significantly less acidic than water, which is around 15.7, or strong acids like HCl, which has a negative pK.
So not super acidic, but more so than hydrocarbons. What kind of base do you need to pull off that proton?
You generally need a pretty strong base. Common choices in the lab are things like sodium hydride, NaH. NaH is nice because when it reacts, it forms hydrogen gas, H2, which just bubbles out of the solution, driving the reaction forward. Or you could use active alkaline metals like lithium, sodium, or potassium metal directly. They also react to form the alkoxide and hydrogen gas.
Okay, strong base needed. But you mentioned phenols earlier have unique properties. Does that apply to acidity too?
Oh, absolutely. This is where it gets really interesting. Remember, phenol, that's where the OH is directly on a benzene ring. Phenol has a pK of about 10. Compare that to cyclohexanol, basically an OH on a non-aromatic six-membered ring, which has a pK around 18.
Wait, 10 versus 18, it's a difference of 8 pK units? That's huge. That's 8 orders of magnitude more acidic.
Exactly. 8 orders of magnitude. It's a massive difference. Phenol is vastly more acidic than a typical alkyl.
Why? What's so special about having the OH on the ring?
It all comes down to the stability of the conjugate base. When phenol loses its proton, it forms the phenoxide ion. That negative charge on the oxygen isn't just stuck there. It can be delocalized, spread out into the aromatic ring through resonance. You can draw resonance structures where the negative charge moves onto carbons within the ring. This delocalization dramatically stabilizes the phenoxide ion. A more stable conjugate base means the starting acid is stronger. Cyclohexanol's conjugate base, the cyclohexoxide ion, has no such resonance stabilization. The charge is just stuck on the oxygen. And because phenoxide is so much more stable, phenol can actually be deprotonated by much weaker bases, like sodium hydroxide, which wouldn't touch a regular alcohol like cyclohexanol.
Resonance stabilization, that makes a huge difference. What about other structural features? Does, like, the bulkiness of the molecule or maybe other groups attached nearby affect acidity too?
Yes, definitely. Besides resonance, there are two other main factors: inductive effects and solvation effects.
Okay, induction and solvation, how do they work?
Inductive effects involve pulling electron density through sigma bonds. If you have electron withdrawing groups near the OH, think electronegative atoms like halogens, they can pull electron density away from the oxygen atom. Take trichloroethanol, for example. Those three chlorines pull electron density quite strongly. This helps stabilize the negative charge on the oxygen when the proton is lost, making trichloroethanol more acidic than regular ethanol.
Okay, electron withdrawing groups increase acidity through induction. What about solvation? You mentioned bulkiness.
Right. Solvation refers to how well solvent molecules, usually water or another alcohol, can surround and stabilize the ions. When an alcohol loses its proton, you get an alkoxide ion, RO. Solvent molecules arrange themselves around this negative charge to help stabilize it. But if the R group is really bulky, like the tert-butyl group in tert-butanol, 2-methyl-2-propanol, those bulky groups physically get in the way. They create steric hindrance. This steric hindrance prevents the solvent molecules from getting close to the oxygen and effectively solvating or stabilizing that negative charge. Less effective solvation means the tert-butoxide ion is less stable than, say, the ethoxide ion from ethanol. And a less stable conjugate base means the original acid, tert-butanol, is weaker or less acidic than ethanol.
So the shape and size really matter for how well the solvent can help out. Fascinating.
It really does. The whole molecular environment around that OH group plays a role.
Okay, so we know what they are, we know about their acidity. The next big question for a chemist is always, how do we make these things? Let's talk about preparing alcohols. What's in the chemist's toolkit?
Well, we've actually touched on some methods in previous discussions. You can make alcohols via substitution reactions. Remember SN1 and SN2. You can react an alkyl halide with hydroxide or water. SN1 works well for tertiary halides, SN2 for primary. Secondary halides can be tricky, often giving mixtures or elimination.
Right, substitution. What about adding to double bonds to alkenes?
Ah, yes. Addition reactions are really powerful ways to make alcohols. There are three key methods you should know. First is acid-catalyzed hydration. You add water across the double bond using a strong acid catalyst, like sulfuric acid. This follows Markovnikov's rule, meaning the OH group adds to the more substituted carbon of the double bond. The catch goes through a carbocation intermediate, so you have to watch out for rearrangements.
Carbocation rearrangements. Always something to look out for. What if you want Markovnikov addition without rearrangements?
Then you use oxymercuration demercuration. It's a two-step process involving mercury acetate followed by sodium borohydride. It also gives a Markovnikov addition of the OH group, but crucially, it avoids carbocation intermediates, so no rearrangements happen. It's a very reliable method for that outcome.
Okay, precise Markovnikov. What if you want the opposite? Anti-Markovnikov, putting the OH on the less substituted carbon.
For that, your go-to reaction is hydroboration oxidation. Another two-step process, first using borane, BH3, often complex with THF, followed by oxidation with hydrogen peroxide and base. This delivers the OH group to the less substituted carbon, and it also results in syn addition, meaning the H and OH add to the same face of the double bond. So between these three methods, you have excellent control over exactly where you place that hydroxyl group when starting from an alkene.
That's a versatile set of tools. Now, another major way to make alcohols is through reduction, right? Taking carbonyl compounds like ketones and aldehydes and reducing them.
Exactly. Reduction here means decreasing the oxidation state of the carbonyl carbon, effectively adding hydrogen across the C-go double bond.
How is that typically done?
But you could use catalytic hydrogen gas, H2, with a metal catalyst like platinum, palladium, or nickel. That works, but it often requires high pressures and temperatures, and it's not very selective. If your molecule also has a carbon-carbon double bond, that will likely get reduced too, which might not be what you want.
Okay, so hydrogenation isn't always ideal. What are the alternatives?
This is where the hydride-reducing agents become incredibly useful. They're much more selective. The two main ones are sodium borohydride, NaBH4, and lithium aluminum hydride, LiAlH4.
Sodium borohydride, NaBH4. Tell me about that one.
NaBH4 is a relatively mild and selective reducing agent. It's usually used in solvents like methanol or ethanol. Its job is to deliver a hydride ion, H, specifically to the carbonyl carbon of aldehydes and ketones. After the hydride adds, a proton source, usually the solvent, protonates the oxygen, giving you the alcohol. The really great thing about NaBH4 is that it selectively reduces aldehydes and ketones, but typically leaves other functional groups like carbon-carbon double bonds, esters, or carboxylic acids untouched under normal conditions.
Selective for aldehydes and ketones. That sounds useful. What about stereochemistry? If you reduce a ketone, you often form a new chiral center.
That's right. If you start with an unsymmetrical ketone, the hydride can attack from either face of the planar carbonyl group. This usually leads to the formation of a new chiral center, and typically you'll get a racemic mixture, equal amounts of both the R and S enantiomers of the resulting secondary alcohol.
Okay, racemic mixture, usually. Now, what about the other one, LiAlH4, lithium aluminum hydride? You said it was stronger.
Yes, LiAlH4, often just called LAH, is a much more powerful and reactive reducing agent than NaBH4. It also works by delivering hydride to the carbonyl group. But it's so reactive that it reacts violently with prochoric solvents like water or alcohols. So you must use it in an inert solvent like diethyl ether or THF, and you have to add it in two separate steps.
2 steps, why?
First, you add the LiAlH4 to your carbonyl compound in the inert solvent. This forms an aluminum alkoxide intermediate. Then in a completely separate second step, you carefully add a proton source, usually dilute aqueous acid, to protonate the alkoxide and give you the final alcohol product. You cannot have water or acid present during the first step.
Okay, LAH is stronger, needs 2 steps, and hydrous conditions first. Does it also do racemic mixtures?
Yes. Generally, if you form a new chiral center by reducing an unsymmetrical ketone with LAH, you'll end up with a racemic mixture, just like with NaBH4.
And does its strength mean it reduces more things than NaBH4?
It does. That's a key difference. LiAlH4 is strong enough to reduce not only aldehydes and ketones, but also carboxylic acids and esters, reducing them all the way down to primary alcohols. NaBH4, being milder, generally doesn't react with esters or carboxylic acids. So the choice between NaBH4 and LiAlH4 often comes down to what functional groups you have in your molecule and what you want to reduce.
That selectivity is really important in synthesis. Makes sense. What about making diols, molecules with 2 OH groups?
Sure. Diols, or glycols as they're sometimes called, can be made in a couple of ways. If you start with a molecule that has 2 carbonyl groups at ditone, for instance, you could just reduce both of them using NaBH4 or LiAlH4 to get a diol. Alternatively, you can make diols directly from alkenes using specific dihydroxylation reactions. There are methods for both syn dihydroxylation, adding both OH groups to the same face, and anti-dihydroxylation, adding them to opposite faces.
And speaking of dials, practically speaking, aren't they used in antifreeze?
They are. That's a perfect everyday application.
Yeah.
Ethylene glycol, 1-2-ethanoediol, and propylene glycol, 1-2-propanoediol, are the main ingredients in most automotive antifreeze solutions. They work because they disrupt the hydrogen bonding network of water, significantly lowering its freezing point. This prevents the water in your car's engine from freezing and causing damage in cold weather. It also raises the boiling point, which helps prevent overheating.
Cool. Literally. Okay. This next method feels like where organic chemistry really starts to get powerful, building bigger molecules by forming new carbon bonds. Get ready for a chemical powerhouse. The Grignard reagent.
Ah, yes, the Grignard reaction, named after Victor Grignard, who won a Nobel Prize for it. It's truly one of the cornerstones of organic synthesis. You make a Grignard reagent simply by reacting an alkyl halide or aryl halide with magnesium metal, usually in an ether solvent like diethyl ether or THF. What you form is an organometallic compound, RMGX, where X is a halogen.
What makes it so special?
The carbon-magnesium bond. Carbon is significantly more electronegative than magnesium, so this bond is highly polarized. The carbon atom essentially carries a partial negative charge, delta minus, and acts like a carbanion. This makes it an incredibly strong nucleophile and also a very strong base.
A strong carbon nucleophile, so it attacks things.
It loves to attack electrophilic carbon atoms, especially the carbonyl carbon of aldehydes and ketones. When a Grignard reagent reacts with an aldehyde or ketone, the R group attacks the carbonyl carbon, pushing the pi electrons onto the oxygen. This forms a new carbon-carbon bond. Then, in a separate workup step, usually adding aqueous acid, the resulting alkoxide ion gets protonated to give you an alcohol. Reacting with formaldehyde gives a primary alcohol. Other aldehydes give secondary alcohols. Ketones give tertiary alcohols. It's incredibly versatile for building carbon skeletons.
Wow, so you can add almost any R group to a carbonyl. What about esters?
Esters react too, but with a twist. Because the initial product of adding one Grignard molecule to an ester is actually unstable and collapses to form a ketone, that ketone then reacts immediately with a second molecule of the Grignard reagent. So when you react a Grignard reagent with an ester, you end up adding two identical R groups from the Grignard, and you form a tertiary alcohol unless you started with a formate ester.
Two equivalents add to esters.
Gotcha. Now, you mentioned Grignards are strong nucleophiles and strong bases. Does that cause any problems? What's the catch with these powerful reagents?
That basicity is the crucial incompatibility. Grignard reagents are extremely strong bases. They're about as basic as the conjugate base of an alkane, which is incredibly strong. This means they will react instantly and irreversibly with any proton that's even slightly acidic. We're talking water, alcohols, amines, thiols, carboxylic acids, even terminal alkanes. If any of these acidic functional groups are present in the reaction flask, the Grignard reagent will just grab a proton from them, destroying itself and forming an alkane instead of attacking your desired carbonyl compound.
Ah, so you can't have any acidic protons around.
Not even a trace of water. This is why Grignard reactions absolutely demand rigorously anhydrous conditions, completely dry glassware, dry solvents. And it's also why the reaction is done in two distinct steps. One, add the Grignard reagent to the carbonyl compound under anhydrous conditions to form the alkoxide. Two, then add the aqueous acid workup to protonate the alkoxide and get your alcohol product. You can't just mix it all together.
Okay, anhydrous conditions are key. This leads perfectly into a really clever strategy chemists use. What if the molecule you want to react your Grignard with already has an alcohol group somewhere else on it? The Grignard would just react with that OH, right?
Exactly. The Grignard would just deprotonate the existing alcohol, and you wouldn't get the carbon bond formation you wanted at the carbonyl group. It's like trying to bake that cake with an ingredient that reacts with itself before it even gets the oven.
So how do you get around that? You can't just remove the alcohol.
You use a protecting group. It's a really elegant three-step strategy. Step one, protect. You temporarily convert that reactive hydroxyl group into something else that won't react with the Grignard reagent. A common way is to turn it into a trimethylsilly ether, an OTMS group. You typically do this using trimethylsilly chloride, TMSCl, and a base like triethylamine. This TMS ether is stable to Grignards. Step two, react. Now that the alcohol is safely hidden or protected, you can go ahead and perform your desired Grignard reaction on the other part of the molecule, like adding it to a ketone elsewhere. Step three, deprotect. Once the Grignard reaction is done, you need to get your original hydroxyl group back. You remove the protecting group. For TMS ethers, this is easily done by adding a source of fluoride ions like tetrabutyl ammonium fluoride, TBAF, or sometimes just mild aqueous acid.
Protect, react, deprotect. That's clever.
It really is. It's a beautiful example of strategic thinking and synthesis. Sometimes you have to temporarily mask or hide one functional group to allow a reaction to occur selectively somewhere else in the molecule. It's a fundamental concept in building complex organic molecules.
Okay, we've covered making alcohols. Now, what about their own reactions? What do alcohols and phenols do? Let's talk substitution and elimination again. We know alcohols can be turned into other things.
Right. Let's start with substitution.
Sure.
We want to replace the OH group with something else, like a halogen, to make an alkyl halide. For tertiary alcohols, this works quite well via an SN1 mechanism using hydrogen halides like HCl or HBr. The acid protonates the OH group, turning it into water, a great leaving group. Water leaves, forming a tertiary carbocation, which is then attacked by the halide ion. But remember the caveat with SN1,
Yeah.
carbocations can rearrange. So always consider that possibility.
Okay, SN1 for tertiary, watch for rearrangements. What about primary and secondary alcohols? SN1 isn't favorable there.
Correct. For primary and secondary alcohols, you need an SN2 pathway. But the problem is the hydroxide ion, OH, is a terrible leaving group. It's too strong a base. So the trick is to first convert that poor OH leaving group into a good leaving group.
How do you do that?
There are several ways. You can react the alcohol with concentrated HBr, which protonates the OH and allows bromide to attack via SN2. Or you can use specific reagents like thionyl chloride, SOCl2, to convert the alcohol into an alkyl chloride, or phosphorus tribromide, PBr3, to make an alkyl bromide. These reactions work well for primary and secondary alcohols via SN2. Another very common strategy is to convert the alcohol into a tosylate ester, using tosyl chloride, TSCl. The tosylate group, -OTs, is an excellent leaving group similar to iodide. Once you've made the tosylate, you can then react it with various nucleophiles like bromide, cyanide, etc. in a standard SN2 reaction.
Tosylate says good leaving groups, and with SN2, we need to remember stereochemistry, right?
Absolutely crucial. SN2 reactions always proceed with inversion of configuration at the carbon undergoing substitution. If you start with an R-chiral alcohol and convert it to an alkyl halide via an SN2 pathway, like using BBr3 or making a tosylate then reacting with bromide, the resulting alkyl halide will have the S configuration. Inversion of configuration. Got it. And this isn't just some abstract lab chemistry, is it? Doesn't something like this happen in our bodies?
It does. A great example is drug metabolism, specifically a process called glucuronidation. Many drugs, or their metabolites, contain hydroxyl groups. Think of morphine, acetaminophen, Tylenol, even the antibiotic chloramphenicol we mentioned earlier. To make these compounds more water-soluble so they can be excreted by the kidneys, the body attaches a large polar sugar derivative called glucuronic acid to that OH group. This happens via a biological SN2-like reaction. The drug's hydroxyl group acts as a nucleophile and attacks a molecule called UDPGA, which contains the glucuronic acid part attached to a very good leaving group, UDP. The drug molecule displaces UDP, forming a glucuronide conjugate. And just like in the lab SN2, this biological reaction occurs with inversion of configuration at the carbon atom of the glucuronic acid that gets attached.
Wow, biological SN2 with inversion. That's amazing. Okay, besides substitution, alcohols can also undergo elimination to form alkenes, right? Yes, dehydration reactions. Again, the mechanism depends on the alcohol type. Tertiary alcohols typically undergo E1 elimination when heated with concentrated strong acids like sulfuric acid, H2SO4. You protonate the OH, lose water to form a carbocation, and then a base, like water or bisulfate, removes a proton from an adjacent carbon to form the double bond. E1 reactions generally favor the formation of the more substituted alkene, that's Zaitsev's rule, and again, carbocation rearrangements are possible. For primary and secondary alcohols, where carbocations are less stable, E1 is slow. You typically favor E2 elimination. To do this, you first convert the OH into a good leaving group, like a tosylate. Then you treat the tosylate with a strong, bulky base, like potassium terbutoxide, to promote E2 elimination, which also generally favors the Zaitsev product, but occurs without rearrangements because there's no carbocation intermediate.
Okay, E1 for tertiary with acid heat, E2 for primary-secondary via tosylate plus base. Now let's flip the script from reduction. Let's talk oxidation.
Right, the flip side. Oxidation involves increasing the oxidation state of the carbon atom attached to the OH group, essentially replacing CH bonds with CO bonds.
How does the outcome depend on the type of alcohol?
It's crucial. Primary alcohols have two alpha hydrogens on the carbon bearing the OH. They can be oxidized twice. The first oxidation step converts a primary alcohol to an aldehyde. If you use a strong enough oxidizing agent, the aldehyde can be oxidized further, all the way to a carboxylic acid. Secondary alcohols have only one alpha hydrogen. They can only be oxidized once to form a ketone. Ketones generally don't oxidize further under these conditions. Tertiary alcohols have no alpha hydrogens, so they generally do not undergo oxidation reactions under typical conditions that oxidize primary and secondary alcohols. The CC bonds are too strong to break easily.
Primary to aldehyde, then maybe carboxylic acid, secondary to ketone, tertiary, no reaction. Got it. What reagents do we use for these oxidations?
The classic strong oxidizing agent is chromic acid, H2CrO4. You usually generate this in situ from sodium dichromate, Na2Cr2O7, or chromium trioxide, CrO3, with aqueous sulfuric acid. Chromic acid is powerful. It will oxidize primary alcohols all the way to carboxylic acids and secondary alcohols to ketones.
Okay, chromic acid is strong. What if you want to stop at the aldehyde stage for primary alcohol? You said that was possible.
Exactly. If you want to isolate the aldehyde from a primary alcohol oxidation, you need a milder, more selective reagent.
Sure.
The most common one for this is pyridinium chlorochromate, or PCC. It's a complex of chromium trioxide, pyridine, and HCl. PCC, typically used in an anhydrous solvent like dichloromethane, CH2Cl2, reliably oxidizes primary alcohols to aldehydes and stops there. It also oxidizes secondary alcohols to ketones.
PCC stops at the aldehyde, that's useful, but chromium reagents, aren't they kind of, well, toxic and environmentally unfriendly?
They are. Chromium's compounds are known carcinogens and generate hazardous waste. This highlights a really significant trend in modern chemistry, the drive to find greener, safer, more sustainable ways to carry out transformations.
So aren't there greener alternatives for oxidizing alcohols?
Yes, several have been developed and are widely used now. Two prominent examples are the Swerin oxidation and the Des-Martin pyridine, the DMP oxidation. The Swerin oxidation uses dimethyl sulfoxide, DMSO, and oxalochloride, COCl2, at low temperatures, followed by a base like triethylamine. DMP oxidation uses a specific hypervalent iodine compound called Des-Martin pyridinane. Both Swerin and DMP are excellent at selectively oxidizing primary alcohols to aldehydes and secondary alcohols to ketones, often under mild, near-neutral conditions and without using heavy metals like chromium.
Swerin and DMP, good alternatives. Do they have any downsides?
Like any reagent, they have pros and cons. The Swerin oxidation famously produces dimethyl sulfide as a byproduct, which has a really foul garlic-like odor. You need a good fume hood. And DMP, while convenient because it works at room temperature, is known to be shock sensitive and potentially explosive under certain conditions, so it needs careful handling. But overall, they represent significant progress towards less hazardous oxidation methods.
Okay. What about phenols? Can they be oxidized? You said tertiary alcohols usually don't because they lack alpha protons. Phenols also lack alpha protons on the ring carbon attached to the OH.
That's a great point, and it's actually quite surprising. Despite lacking that alpha proton, phenols do oxidize quite readily, much more easily than tertiary alcohols. They typically oxidize to form compounds called benzoquinones. These are molecules with a cyclohexanidionase structure.
Benzoquinones, are they important?
Incredibly important, especially biologically. Quinones have a fascinating and crucial property. Their redox chemistry is reversible. A quinone can be easily reduced by adding 2 electrons and 2 protons to form a hydroquinone, and the hydroquinone can be easily oxidized back to the quinone. This reversible electron and proton transfer is absolutely central to how our cells generate energy through cellular respiration.
How does that work?
There's a class of quinones called ubiquinones, also known as coenzyme Q, that are, as the name suggests, ubiquitous, found in virtually all aerobic organisms. Ubiquinones act as mobile electron carriers within the inner mitochondrial membrane. They shuttle electrons along the electron transport chain, ultimately helping to convert the energy stored in food molecules into ATP, the main energy currency of the cell. Part of this process involves the quinone accepting electrons and protons and eventually helping to reduce molecular oxygen to water. It's a fundamental process of life, and the discovery of its mechanism earned Peter Mitchell the Nobel Prize in Chemistry.
Wow, from simple phenol oxidation to the energy of life. That's quite a connection. And speaking of biological oxidation, let's finally circle back to that hangover we started with. We've learned the chemistry, so how does it apply?
Right. It's all about biological oxidation by enzymes in your liver, primarily alcohol dehydrogenase and aldehyde dehydrogenase, using NAD+ as the oxidizing agent. Let's quickly contrast methanol and ethanol. As we said, methanol is toxic. Alcohol dehydrogenase oxidizes it first to formaldehyde, which is very toxic. It cross-links proteins. Then aldehyde dehydrogenase oxidizes formaldehyde to formic acid. Formic acid is also highly toxic. It disrupts mitochondrial function, leading to metabolic acidosis, blindness, and potentially death.
And the treatment is? Ethanol.
Counterintuitively, yes. Ethanol competes with methanol for the active site of alcohol dehydrogenase. By giving ethanol, you slow down the formation of those toxic metabolites, formaldehyde and formic acid, allowing the methanol to be excreted unchanged before it can cause too much damage. Fomazole is another drug that directly inhibits the enzyme.
Okay, so that's methanol. Now, what about ethanol, the stuff people actually drink?
Same enzyme system. Alcohol dehydrogenase oxidizes ethanol first to acetaldehyde. Acetaldehyde is the primary culprit behind most hangover symptoms: nausea, vomiting, flushing, headache. It's significantly more toxic than ethanol itself, though less acutely dangerous than formaldehyde. Luckily, we have another enzyme, aldehyde dehydrogenase, ALDH, which quickly oxidizes acetaldehyde further into acetate, acetic acid. Acetate is essentially non-toxic, can be readily used by the body in energy metabolism.
So the hangover feeling is mostly due to the buildup of acetaldehyde before it gets converted to harmless acetate.
Exactly. How quickly and efficiently your body, particularly your ALDH enzyme, can clear that acetaldehyde determines, in large part, how severe your hangover symptoms are. Genetic variations in these enzymes explain why some people tolerate alcohol better or worse than others. Binge drinking overwhelms this system, leading to acetaldehyde buildup.
So there you have it. The science behind why you feel rough the next morning, responsible drinking, staying hydrated, and definitely avoiding binge consumption are really the only scientifically sound ways to prevent a hangover. Your body just can't process that much acetaldehyde quickly.
Precisely. No magic cures, just biochemistry.
Okay, we've covered structures, properties, acidity, preparation, and reactions. Let's zoom out now to the bigger picture. Synthesis strategy. How do chemists put all this knowledge together to actually build complex molecules? This feels like the real art of organic chemistry.
It absolutely is. When you're planning how to synthesize a target molecule, you're usually grappling with two main challenges. First, changing the carbon skeleton. Do you need to make the molecule bigger by adding carbons, or maybe smaller by breaking bonds? Second, changing functional groups. How do you convert the functional groups you have in your starting material into the ones you need in your product?
Skeleton changes and functional group changes.
Exactly. And to navigate the functional group changes, it helps to think of that map we've implicitly been building. Imagine a map connecting the different families of organic compounds: alkenes, 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 alkylides, alcohols, ketones, aldehydes, carboxylic acids, esters, and so on. All the reactions we've discussed, oxidation, reduction, substitution, addition, elimination, are the rows on that map. They allow you to travel from one functional group location to another. Understanding this map, how the different functional groups interconvert, is key to thinking like a synthetic chemist. You see the connections, the possible pathways.
And for changing the carbon skeleton, making it bigger, those Grignard reactions we talked about are key, right?
Indispensable. Grignard reactions and similar organometallic reactions are the primary tools chemists use to form new carbon-carbon bonds, allowing us to construct larger, more elaborate molecules from smaller, simpler building blocks.
So the real art comes in combining these strategies, using functional group interconversions and carbon bond-forming reactions together.
Precisely. Often, the transformation you want to achieve isn't possible in a single step. You have to combine multiple reactions strategically, like your earlier example, converting an aldehyde to a ketone. You can't do it directly, but you can do a Grignard reaction on the aldehyde to add the extra carbon and make a secondary alcohol. Then, you oxidize that secondary alcohol to the ketone. Two steps, combining CC, bond formation, and functional group manipulation. It's like solving a puzzle.
That makes sense. It's like planning a route with multiple stops.
And a powerful way to plan that route is using something called retrosynthetic analysis.
Retrosynthesis, what's that?
Instead of thinking forward from starting material to product, ABC target, you work backward from the target molecule. You look at the target and ask, what reaction could I have used to make this molecule in the last step? And what would the precursor molecule for that reaction look like? You keep breaking the molecule down into simpler precursors, step by step, using known, reliable reactions until you reach readily available starting materials. It's symbolized by a special open arrow. At each backward step, called a disconnection, you carefully consider things like regiochemistry, where groups add, and stereochemistry, the 3D arrangement, to make sure the proposed forward reaction would actually work as intended. It turns complex synthesis problems into a series of more manageable steps.
Working backward from the goal, that sounds like a really logical way to plan.
It's the standard approach used by synthetic chemists worldwide.
Okay. And with that, I think we've completed our deep dive into alcohols and phenols.
Wow. We went from the basic structure of an OH group all the way to drug metabolism, energy production in our cells, and even the strategies for building complex molecules. It's really clear how fundamental these compounds are.
Absolutely. Understanding their structure, properties, how to make them, and how they react, including all those specific named reactions and reagents like Grignard's, PCC, lyolH4, teselladates, fusilates, it's truly crucial for anyone studying or working in organic chemistry. Hopefully, this deep dive gives you a really solid foundation and maybe a new appreciation for the molecular world all around us and even inside us. These concepts pop up constantly in problem solving and understanding more advanced topics. Definitely. So, as a final thought for everyone listening, consider just how many everyday products, materials, medicines, and biological processes rely on that delicate balance of properties and reactivities of alcohols and phenols we've talked about today. From the antifreeze in your car to the capsaicin in your food to the way your body gets energy. What other surprising connections might you find if you start looking at the molecules you encounter daily? Thank you so much for joining us on the deep dive. We really hope this has been an illuminating journey through the world of alcohols and phenols. We look forward to exploring more fascinating chemistry topics with you next time.